Okay, so problem number one asked for a Riemann sum midpoint approximation, right? So that means that, if we're going from -1 over here, let's say -1 is there, and let's say 5 is here, and we want three, where is it again? Three subintervals, right? Three subintervals. So that means we're going a distance of 6, right? So 5 minus a -1, and then you divide it by how many subintervals you have. So our delta x divided by the number of intervals, and that would be 6 divided by 3. So we've got 2. So we want to go from -1 over to 1. I don't know if this is going to come out so great. And then we'd go from 1, oh geez, to 3. These are supposed to be equally spaced. And so now, look, the distance that we're going is 2. What we need to do to find a rectangle is we need to know the height of the rectangle, right? And the height of this rectangle is going to be calculated at the middle of the interval. So what I want to do is I want to find the middle, and I want to go up that height, right? Now, if it said a left-hand rectangle, I'd be going up on the left side of the rectangle. If it said a right-hand rectangle, I'd go up on the right side. So that is at 0, the midpoint, right? And the midpoint of this one is at 2. And the midpoint of this one is at 4. So when you look over here, that's why I'm calculating the y value at 0, 2, and 4. And then I'm multiplying by 2 to get all, I've just factored out the 2, or distributed out the 2 out front for the width of my rectangle, right? So the width is 2 and the height is calculated at that midpoint. So that number comes out to be 732. The definite integral I just calculated on my calculator. It doesn't say in here that I need to. I mean, it does say show work, but I think the Riemann sum is enough work, and then my setup for my integral is enough work. So I think it'd be okay if you just set up your integral, and then that's that answer. So what's the difference between those two? It's 42. So the error of our Riemann approximation is 42 off of the actual area of 774, right? All right, number 2 was kind of a tricky one, right? Like, you could do number 2 without any calculus, because there's a physics equation that looks like this. The position of some object, if it's like in free fall, or any kind of motion, is affected by gravity. Vertical motion is 1/2 the acceleration of gravity times time squared, plus the initial velocity times time, plus its initial position. So they're telling us all those things: the acceleration of gravity, the -32, right? The velocity of what is it, 154, -154, and the position of 100. The guy is throwing the ball from 100 feet up in the air, 100, whatever it is, feet. So they're wanting us to show a little calculus on this, though. So the antiderivative of acceleration gives you velocity. The antiderivative of velocity gives you position. So when I do the antiderivative of -32, I get -32 plus c, and the c is really our initial velocity, because when you stick a 0 there, the acceleration component goes to 0, and you're left with whatever they told you the velocity is, right? So that's the kind of work I'm doing right here. Once I get my equation, it wanted to know, let's see, what was it on this one? Oh, shoot. Oh, how long the mosquito has to live, right? So we want to know when this is equal to 0. And I just stuck it in the solver. And that gave me the 0.6611, right? And then it says, what was the baseball's average velocity during the time of flight? I think you could just take the distance that you went, 100 feet, and then divide it by the time it took for the ball to fly that far. And that's going to be your average velocity. So you don't really need to do, an integral of the velocity. You could take an integral, but you don't really need to do that. What you might be saying, what's he talking about? You could go -32t minus 154, and you go from 0 to 0.611 seconds, and then you would divide by 0.611, the distance that we're going. But that should come out to be the same as what we got going on over here. You can try it out and see. but this number should give you 100, and 100 divided by 0.611. So sometimes when people see that average velocity, they think we got to do an average value problem, but you can kind of avoid it on this one. Let's go to problem number 3. 3 is a tricky one. You got this differential equation like this, and the idea is to separate the variables, right? So I separated the variable. The dt is now on this side. The dn's on this side with n. You take the antiderivative, and now we got to find our two constants. We got to find the k value and the c value. When you plug in 0 for time and 10 for n, you get a c of 22. Okay, you could do that work right here, right? If you plug a 0 there and you plug 10 right there, you get definitely 32 minus 10 would be 22. See where that 22 comes from? And then e to the 0 power gives you just the c value. So c equals 22. Okay, now when you plug that 22 back in, you got to find the k value. So if I put 20 and 20 in, that's what I'm doing right here, you're going to be able to find the k value by following those steps right there. And it comes out to be negative 0.03. And I'm trying to show people that you'd want to store that into, your k value. So it might be best right here to put like a double arrow or something like that, like this, stow, and then you put, k or something like that. So when you write the equation over here, right, you're telling people, look, I stored the k value in my calculator of negative 0.03, right? All right, number 4. Let's see on number 4. This one was, from 0 to some number, the integral is going to be equal to 12. So you take the antiderivative and you plug in the a into your antiderivative right there, and you plug in 0. Obviously, that goes to 0, right? And then you're going to set it equal to 12. And I use my solver feature on my calculator to find that. You could graph it, and it might actually be safer to graph. And here's why it might be safer. Because what you're going to see is something like this, okay? It goes like this, and by 0.6 or 1.236, the area is 12. Now it keeps going up. The area is increasing right over here. So we're going past 12 to this point, and then the area starts, decreasing because we're below the x-axis. So out here you get another answer, and I know my scale's not super good again, but you get another answer of 3 for where the area goes back to 12. But you don't want the 3 value because it says the first quadrant. Okay, so this is now in the second quadrant. So we only want the area in the first quadrant. All right, number 5. I think number 5 is on the next page. Yes, it is. I'm taking the antiderivative of this guy. I'm doing use substitution. So study this a little bit. Study this answer. If you see something not right, let me know. Or if you have a question about it, ask me on Tuesday. Number 6, I'm doing the antiderivative again. I'm doing use substitution again. I end up with that guy all the way down here. You can pause the video as I'm showing you all my steps on use substitution. All right. Number 7, I'm doing integration by parts. You have to show this work when they got this in bold font right here. You got to show this kind of work right here. And integration by parts works like this. You got your UV right here. Let me put that right here, u times v, and then this is your minus v du right over here. So we go u times v, and then you go v times du. All right, so when you do that work, this is what happens. I got my uv. I got it right down here. I didn't notice that. So I guess I'm not all the way done yet. Why didn't I write maybe I put my answer down here in the box. Let's see if I put the answer in the box. There it is. There it is. Okay. So that's what I did. So yeah, right here, there's my answer. Number 8, partial fractions. Oh boy, partial fractions. So how does this work again, this heavy side technique? What you want to do is you want to break up this guy into 2 fractions, right? A and x plus b over x plus 1. And we said, look, if we're worried about when x is 0, I could multiply both sides by x. And if I did that, if I multiply by x over here, this x would cancel out with that x. This x here would cancel out with that x. And then the x wouldn't cancel out over here, right? So when I put 0 now, when I put 0 in for my rest of the stuff, watch what happens. If I put 0 here and I put 0 here, I get negative 3 over 1. Okay, so I get negative 3 over positive 1. And that's equal to a, and then plus, well, I'm putting 0 there, so this is all gone. And we just have an a. So that's why covering up, let me undo all my writing here. Like covering up, there we go. Okay. Like this guy, just ignore it and put the 0 in the other two spots. That's going to give you the a value. That's giving me this number right here. And when you put negative 1 into this guy, okay, so let's undo my little scratch out. If I put negative 1 here, now I got, I'm sorry, I'm doggone it. I'm covering that up because I'm not going to put negative 1 there. I'm going to put negative 1 over here. And so I get negative 1 minus 3. That's the work I'm trying to show right here. Negative 1 minus 3 is negative 4. Divided by negative 1 gives me a positive 4. That's my b value. Okay, so once you get these two down, then you got natural logs working for you for the antiderivative. All right, let's see, where are we? I'm on number 8. I think 9's on the next page, right? So yeah, so my answer, if you want to, pause the video, check out my answer. That might be a good idea. Number 9. Okay, trig substitution. All right, so I set up my triangle, and I've got addition in here with the square root, so that must mean we're looking for the hypotenuse. So one leg must be 4, because 4 squared gives 16. The other leg has to be x. I set up my basic trig function. The most basic one might be this one, tangent of theta equals x over 4. The secant would be the big square root over 4, right? And then what am I going to do over here? I'm going to replace. So, well, first I took the derivative of both sides here. Okay, that gave me 4 secant squared theta d theta equals 1 dx. And so I want to replace the dx that's sitting right there with all this stuff, 4 secant squared theta d theta. Bam. And I replace the denominator by what the square root's equal to. Well, the square root would be equal to 4. Ooh, I have a 16 right there. Let me scratch that 16 off. 4 secant theta, right? So I'm multiplying both sides by 4. So I put a 4 right there, 4 and secant theta, because that's equal to all of this stuff right here. All right, now some secants cancel out, don't they? So there's like a secant here that's going to cancel with one of these secants up here. That's why I got a slash through the squared. And there's a 4 that divides into the 4. So now we're down to secant theta. And the antiderivative of secant theta is natural log secant theta plus tangent theta. This is one that it's hard to remember for me. So I would put this on a cheat sheet if I was you, or in your notes, okay? And also put maybe cosecant and maybe put down whatever else you might need, like tangent or something. I don't know. So let's look down below number 10. Oh, by the way, there's my final answer right there. I have to substitute back in for my secant and my tangent. So you look back over here and say, what's tangent equal to? X over 4. What's secant equal to? Square root of all that business all over 4, right? So here it is. I'm substituting back in for my secant and my tangent. Number 10. Yeah, it looks like it converges because this guy's getting super close to 0, right? That's what they first want you to do, show a little graph. Then you set it up like this. Limit as b goes to infinity. So we're going to go from an integral. Notice I left off my limits of integration here because I switched my unit or my variable. So I had x's, now I've got u's. I could take 0 and plug it in and get 4 and put a 4 over here, I guess. And b is going to infinity, so it doesn't really matter. I mean, I could still have my b up here. That's totally fine. But I didn't do that. I just went through, I took my antiderivative with the u, and then I plugged the x's back in. And I want to evaluate that from 1 to b. So when I plug b in, where'd that go? Right here. I didn't really have my b plugged in somewhere, but you can imagine the limit as b goes to infinity. If b was sitting here, we're going to have something going to infinity down the denominator. So I get a 0. And then if I plug 1 in, I get 1 plus 4 is 5, and that's 25. 25 times 2 is 50. That's where the 50 comes from. So I'm plugging the 1 in. There's also a negative there, right? So it's negative 1 over 50th. And then I got to take an opposite of that and then multiply by a half. So that becomes positive 1/100th. And if you looked at it on the graph, if you have the calculator do a function integrate on this guy, and you go from 1 out to, I can't remember exactly where 1 was on my graph, but let's say it was like here. If you go from 1 out to even like 10 or something like that, the approximation on the calculator is really close to 0.01. What I'm saying is if you go from 1 to 10 of this guy right here, x over this x squared plus 4, x squared plus 4 squared dx, it's something like 0.00998 or something like that. So you can see it's getting really close to 1/100th, a hundredth. All right, number 10 is out of the way. 11, I think, is on. Oh, no, 11. Wait. What's going on here? Hold on. That's not number 10. That's number 10. Oh, yeah. This program's weird. It has another picture of the same document down below. So 11 is on the next page. I want the area of this region right here, the region between the curve and this curve down here. So I'm labeling it on my graph. Y1's this guy, Y2's that guy. So I wanted to see, this is the kind of work I want to see on the test. Okay. You don't have to take the antiderivative of each one of these guys. We've already done those antiderivatives back a few problems ago. So if you just set it up like this and give me a decimal approximation, I'm totally good with that. Okay. On number 12, they don't even want you to find the volume. They just want you to set it up, don't they? It says you may use your calculator to find the intersection points nearest. You do not need to compute the volume. You just need to set it up. So here's the basic idea with a washer technique. And then my bigger function out here is the one that is an exponential function. The smaller one is the x squared function. We also are rotating around the y-axis, which might be the way it goes on the final. So you want to know what I'm doing over here. I'm converting from my equations from y, solve for y, to solve for x. So now I've solved it for x on this equation. Move the 3 over, take the square root of both sides. And then for the exponential function, you're going to divide by the 0.2 or multiply by 5, however you want to think about it. And then take the natural log, right? They're converted to logarithms. So my x is equal to natural log of 5y. And then I put those down here. The one thing the calculator was kind of balking at was, I think, having this square root here and then squared. It was like freaking out, and it wasn't giving me an answer. So really, you probably should just square this before you try to evaluate on a calculator. But it does say you don't need to evaluate. But I think if you try, I think you'll get 1585 and get your calculator to do it. Number, let's see, 13. Did I skip 12? Let me make sure I got this all squared away. No, that was 12. Okay. And this is the answer they're looking for on 13. Oh, yeah, this is the last one. I like to draw a little thin circle here, a little thin disc, if you will. And I want to find the volume of that disc and then the weight of that disc, because the weight needs to be lifted up out of the cone a certain height. Okay, that would be the work calculation. So I find the area of the circle. I'm going to say that my distance from the center down to that disc is x. And then what I did was, then this part down here would be 20 minus x. And so I've got 3 over 10, because 6 over 20, the radius over the height, is the ratio of any radius to whatever it takes to get down to the point, right? So like this is my radius, and this is the distance down to the point. So what I'm doing is I'm saying the radius over 20 minus x. I probably should have a little r right here. Okay, let me put that in there. And I need to get an equation for r in terms of x so that I could, write this circle up. So that's what I did. It looks kind of complicated, my formula. And so I wasn't super happy with my first way of setting up the drawing, because there's always multiple ways to set up the drawing and think about a problem. And so I'm going to try a different way on this one over here. So if this way doesn't make sense, then you let me know. So I've got the area. Okay. If I want the volume, I take it times some thickness, some super thin thickness. Then if I want the mass, it told me I got like 1,000, 1,000 kilograms per something or other. 1,000 kilograms per cubic meter, right? So we're multiplying by 1,000 because this was in cubic meters. So if I multiply by 1,000, now I got the mass. If I multiply by 9.8, now I got the weight. I know those are physics things. It tells us up in the directions. You can just multiply by 9,800, right? And so now I want to take all of that and I want to lift that up. See, that's the weight of that one super thin washer or disc. And I want to lift it up x plus 1. So when I look back at my drawing, why am I lifting that up x? Well, it's the distance up to here. And then I got to lift it one more, it told me in the problem, right? So all of that goes in your integral, and I'm going to lift it from 6 to 20. So where does that 6 to 20 come from? Let's look again. Well, it told me that the water level was only 14 meters up, and it's a total of 20 meters. So that's a distance of 6. So this disc up here, if we calculate a disc right there, it has to be lifted up 6 to this x value right here, right? And so the x, I should say like this. I should say the x is going to go from 6. This is the first disc that we run into, all the way down to 20. That would be the bottom disc right down here. Sorry about that. I don't think I made that super clear right there. That's why I'm going from 6 to 20. On this one, it's going to change a little bit. So this is the way I think, on second thought, I wish I would have done this the first time. I would have made this x right down here. Okay, so let's talk about the limits. Let's kind of go in reverse order for a second. Why am I going from 0 to 14? Well, the smallest little disk would be down at the bottom when x is 0, and the biggest disk would be up here when x is 14. So that's why I'm integrated from 0 to 14. Now, I'm setting up how far you have to lift a particular disk a little differently than I was doing over here. So let's say I take this random disk right here that's up x, right? Well, how far do I need to lift it up to get to here? Well, that would be 20 minus whatever this distance is, right? So 20 minus x. But then I got to lift it up another meter because it told me it's a meter out of the cone. So that's why I put 21 minus x. So this right here is the distance we have to lift, or the distance we have to apply a force to. So that's my distance. Okay. And then all of this stuff is my force. So it came out a little bit easier when this is just x, because when I relate r to x, it's the same as relating 6 to 20, because 6 and 20 are in a similar triangle as r and x. So that's why I'm doing r over x equals 6 over 20. And then I multiply both sides by x, and I reduce my fraction down. So 3/10 x. I'm going to plug that 3/10 x right here and square it, because that's the radius squared times pi, right? So that's the area of that little disk right there. Then I multiply by 9,800 to get the force, or the weight of that disk. And then, the dx part is for the thickness of that disk, right? So that gives me a volume. So this is the area times the thickness gives me the volume, and then times the 9,800 to get the weight. What? All right. Well, good luck on this problem. Good luck on the test. I appreciate you following along with my video. Thank you very much.